laziness for a particular aspect of permutation groups. Namely, as I'm constructing a permutation group, the usual construction is to start with this empty group object, and then we have our set of generators, and what we do is we add a generator one by one. After we add the first generator, this group object kind of flourishes, a lot of stuff is added to it. In fact, we can look at the code real quick. Group.list. We can see that when we do this add generator thing to a group, all these things are being done. We're recursively calling this function update. So first we're adding this permutation to this set right here. We're updating the transversal system, where if we scroll down, update transversal, that's setting some new things. And then again, we're calling add generator. So it's this ping pong between these two functions. And every time we add a generator, it goes to this ping pong and updates the structure. A problem sort of arises if we want to decompose an element of a permutation group down to its constituent generators. There's this, when we update these data structures, this permutation group data structure, there is no easy way to reverse back to the constituent generators. We can reverse back to the so-called strong generating set, which is this SGS right here. We're producing a new kind of basis for the group called the strong generating set, basis in the linear algebraic sense. However, we generally, I mean, the SGS is very useful, but generally we have our original set of generators, which is, you know, right here, that we wish to represent our permutations as in this group. So what we can do, the general strategy would be, as we're building up this data structure, we also maintain something like we construct a homomorphism from a free group to our permutation group, and then we do all our operations in parallel. We do operations in our free group on these elements, like this, for example, this perm compose right here, and this perm compose and perm inverse right here. We do all of our operations in parallel with another free group. So we'd have new perm here, and then we'd have a free group element kind of right below it. And we kind of record all the operations that are being done in a lazy sense. So if we know how each element within our permutation group data structure was constructed by way of recording all the compositions and all the inversions that happen, then what we can do is when we look at our strong generating set, which I said we can take a permutation and decompose it into this basis set, we can look at how each of these elements were constructed out of the original generators. And since we can do that, then we can take our original permutation and divide them into our original generators. That sounds a little complicated, I think. Just the idea is, if we know how everything was created based off of the original generators, and if we record that, then we can kind of do a replay, and when we decompose a permutation in terms of its strong generating set, we can go back and actually decompose it into its original generators. Not very efficiently, but we can at least do it. So that motivates the definition of some sort of lazy group almost. And a free group is mostly like that, but we want to build a new data structure. Ideally, that can work with any kind of group, not just a free group, but it'll primarily work with a free group. The idea that we can compose and invert, and all of those operations are truly, honestly lazy operations. I haven't thought about how I would implement that completely, but I have one idea which I'll go off on. So I'm gonna, let's see, delete all of this stuff down here. I'm not going to commit the free group stuff yet because there's some cleaning up I want to do. I think this code kind of looks ugly. It's repetitive. You know, like Fare said in the chat, you know, it might be worth adding an element valid P to the protocol It's just this code I don't think is very clean for a concept that should be ideally very clean. So anyway, this whole lazy group business is a concept in computational group theory called straight line programs. So I'm going to create something called straight line program.lisp and start hacking on that. So straight line program.lisp, copyright C2015. Let me check IRC before I actually Alright, what's up on IRC? Oh, okay. Nothing. Alright. So, the way I imagine straight line programs, again, I don't want to make a new kind of group. I don't want to make something called a lazy group, which satisfies the group protocol and so on, because that means I am forced now to create some group homomorphism between that lazy group and our target group that we're actually working with. And I don't want to try to maintain both those things necessarily in parallel. Ideally, I could add a new kind of functionality that lets me create straight line programs within any kind of group context. So the way I imagine this is it's very similar to a free group, but this time we maintain sort of machine identity. So I'm just going to start kind of writing something and we'll see where it goes. I'm actually going to do let's see, UL quick load. What should we load? CL algebraic data types. Oops, there's no S in that. So I'm going to just call it an SLT, a straight line program. And the idea of a straight line program is that we kind of lazily represent various operations that happen. So maybe we represent composition. I'm actually going to prepend these, I think, SLT composition. Maybe something like this. Yeah. Of some elements, which is just, I'm just going to say T, and then an SLT inversion of some element T. SLT element of T. So there are three things that we could possibly have here. Yes, I should say SLP, not SLT, actually. I don't know why I was thinking T, but I guess it was. So, so yes, this is our straight line program. Straight line program. And so I'm going to compile this now, and now if we do SLP element of 5 and SLP composition of that and SLP element 6, then we get, it's just a lazy thing. It's not actually evaluating anything. If we do SLP inversion, we just get that nothing is actually getting evaluated here. So we could stratify these types a little bit. Really, this should be an SLP, this should be an SLP, and an inversion should be an SLP, and the element is the only thing that identifies. This is this element here, or this part of the data structure, is the only part of the data structure where we would actually introduce elements from another group. So we can okay, so we have this, and now we want to be careful about data circularity and stuff like that. We might not actually need to do anything in that respect. Let me think. So we want to be able to save as much data as possible. Ideally, 2 SLP elements, like 5. If I create, elements, there's no T in there, or no S. Ideally, if I do this twice, it's not allocating the same thing, but if I do EQ of SLP, I can just do EQ of this and this, you'll see that they aren't the same, but ideally they are the same. So another characteristic of straight line programs is it's very symbolic. We are symbolically attaching a name to things. So I actually should augment this data structure with SLP symbol, and I'm going to ensure that that is a key. I'm going to say it's just symbol. So essentially what happens, and I'm not sure if this will work out 100% correctly, but the idea is that we can say something like x1 equals a free group element 5, x2 equals a free group element 6, x3 equals the composition of x1 times x2, x4 equals I don't know, the inverse of x3, along with, times the element 2 times, I don't know, x2, or something like that. And this is where the name straight line program comes from. The idea is that there's no branches in here. Execution flows simply downward. And each new assignment, quote unquote, is a new thing. We can't do, again, x3 equals here because we're reassigning this. So in this sense, it's very similar to things like representation of SSA, single static assignment. It's similar to single static assignment. It's similar to what's it called? There's a name for programming where you only assign once. I don't remember off the top of my head what it is. But that's where the name straight line program comes from, is that we're kind of essentially, in some sense, constructing a, quote, program, unquote, which represents group elements. So what we can do here, let me recompile this, so we can do SLP symbol now. We can do like X, for example. So let me put these, oops. So once we have an element, we will want to be able to normalize. But before we can normalize, like I said, we're assigning symbols. So we need some way to remember symbols that we've already well, we need to assign them somewhere, meaning we need to make this assignment x2 to 6 somewhere. So I'm going to make a new data structure called first let me rename it. So